For those of you that are not that familiar with UCAR, UCAR is a not-for-profit corporation of 117 member universities that grant advanced degrees in the atmospheric and related sciences. UCAR also manages the National Center for Atmospheric Research, which is funded by the National Science Foundation. And so the research that we do at UCAR helps to inform decision makers, as you'll be hearing today, and provides benefit back to society to improve our predictive capabilities in areas such as weather, water, climate, and solar storms. Several times a year, we bring together members of the research community to the Hill to discuss the latest science in areas of importance to policymakers. And in fact, the last Hill briefing we did was on fire weather because we foresaw, unfortunately, the bad fire season ahead of us. This brings us to today's topic. Our community often speaks about the challenges of R2O, that is research to operations. And over the past year, I've been highlighting the opportunities to be had in R2I, research to industry. And so today we'll hear from three experts about this important topic, moving research findings from the lab to the market. Federally funded research is the engine powering a growing multi-billion-dollar weather forecasting industry. In our case, the investment by the National Science Foundation in basic research has enabled private weather companies to make increasingly accurate and targeted forecasts for consumers and businesses. These forecasts, along with those by the National Weather Service, play a vital role in predicting and protecting life, property, supporting national security, and enhancing our national economy. Improving weather forecasts and reestablishing U.S. preeminence in numerical weather prediction is a high national priority. Weather and climate disasters cost us billions of dollars every year. In just the past few months, we've seen the damages from hurricanes Harvey, Irma, and Maria, and the projections are upwards of about $200 billion in losses. To better protect society, federal agencies, universities, and the private sector are working together in this three-legged stool sort of concept to develop forecasts that have unprecedented accuracy and detail. Improved forecasts build on strategic government investments in satellites, land and sea-based observations, computer models, and ever-increasing high-performance supercomputing. In addition to better forecasts of storms and everyday weather, scientists are working on one of the great next challenges of seasonal, subseasonal to seasonal prediction. By predicting these weather patterns 2 weeks to 3 months in advance, forecasters can provide vital intelligence for business leaders in agriculture, energy, insurance, transportation, and virtually every other economic sector. Better forecasts provide a major economic return to the nation, and these investments that taxpayers are making in basic research are paying off many times over by keeping our nation safe and more prosperous. And so our panelists here today will talk about major new advances in federally funded research and how they offer the potential for improved weather forecasts. So on my right, and first off, will be Dr. Rebecca Morris, who is a senior scientist at our National Center for Atmospheric Research and Deputy Director of the Center's Mesoscale Microscale Meteorology, or M-Cubed Lab. Rebecca is an expert in weather forecasting and risk communication with an emphasis on high-impact storms, including hurricanes, floods, and tornadoes. Her research focuses on the predictability of weather hazards, the communication and interpretation of hazardous weather risks, and how decision makers use this important information. Next, Dr. Fuqing Zhang is professor in the Department of Meteorology and the Department of Statistics at Pennsylvania State University. He's also director of the Penn State Center for Advanced Data Assimilation and Predictability Techniques. Professor Zhang has made significant contributions to our fundamental understanding of atmospheric predictability and the limits of prediction. He uses radar, as you'll see, and satellite observations, and he assimilates or merges these observations into advanced computer models in innovative ways that have led to significant improvements in the analysis and forecast of severe weather and tropical cyclones. And our last member is Mary Glocken, known to many of us as the Director of Science and Forecast Operations at the Weather Company, an IBM business. Mary oversees the Weather Company's global forecasting science, services, and development. She also manages the company's relationships with national and international government agencies, academia, and the private sector weather providers. Mary's very distinguished career spans 20 years in the National Weather Service and a 5-year tenure as Deputy Undersecretary of Commerce for NOAA. And we will begin with Dr. Rebecca Morris. Rebecca.
Okay, so thank you for inviting me to speak here today. And I'll be talking about some of the ways in which scientific research investments over the last few decades have enabled the weather forecast that we receive today that benefits society. And as we all know, weather forecasts aren't perfect. They still have errors. And so I'll also be talking about some of the major research innovations that are going on now that are going to continue to improve weather forecasts in the future, both in the public sector and the private sector. So this slide comes from a research paper by Bauer et al. In Nature, where they talk about this quiet revolution of modern weather prediction. And the reason they call it a quiet revolution is because while all of us have been going along in our everyday lives, behind the scenes, advances in science and technology have been improving the weather forecast that we receive. If you look at this graph, you can see forecast skill is on the y-axis that goes up. So forecast skill improving on the y-axis, and on the x-axis you can see as time increases over the decades, the forecasts have gotten dramatically better. Two things to note is the first, on the left-hand side, you can see that several decades ago, the Southern Hemisphere forecast used to be significantly worse than the Northern Hemisphere forecasts. And then as we got better in assimilating or bringing data from satellites into the models, then the Southern Hemisphere caught up with the Northern Hemisphere. But as Fuqing will be talking about later, there's still a lot of room for improvement in terms of how we incorporate the data into the models. And then if you look at this, you can see that a 5-day forecast of today is about as good as a 3-day forecast was 2 decades ago. So there's a lot of improvement in weather forecasts. And this graphic shows forecasts kind of averaged overall, but as Fuqing will also talk about, there's been a significant improvement also in extreme weather forecasts for hazardous weather and so on. And so this improvement in forecast is enabling the decisions that we make today. It's enabling a lot of decisions to protect life and property and also to enhance the national economy. And so next I'll talk about some of the innovations that are going on now that will continue to improve weather forecasts and reap societal benefits in the future. So what are some of the next revolutions in science that's going on right now that will help to improve weather forecasts in the future? The first thing that I'll talk about today is global multiscale weather prediction modeling. And the goal of that is to extend the finer scale forecast that we get today to longer lead times. And this is important because people really need more information further in advance in order to make decisions. For example, for hurricane evacuations, that planning starts 4, even 5 days in advance or longer today. Another theme that I'll talk about is expanding weather prediction to forecasts of hazards and impacts. And this is important because in order to make decisions in the public sector and in industry, people need to know about the weather that's going to happen where they are, so the details of the weather. And this is another important evolution as the skill in modeling improves with that. And then another area that I'll talk about is about the integration of social sciences with meteorology to improve forecast creation, communication, and use. This is another theme in the weather community today. How can we take the knowledge that we can learn about how people use information and interpret it to improve how we forecast? So first, just briefly, why is finer scale weather modeling important? On the left here, you see an example of what a model grid might look like with 6-kilometer spacing relative to a cloud. On the right, you can see if you have a smaller grid spacing, you can really represent the weather processes that are going on in the model a lot better. And you can also better predict the details of the weather that happen where people actually are. This requires a lot of computing technology. So as you increase the resolution, you need a lot of computing power, more than double, much more than double in order to be able to run the weather model in a timely manner to produce better forecasts. And there's a lot of scientific research that goes on behind the scenes in order to represent the processes in the model, in order to do the modeling, in order to bring the data into the model, the observations, to improve the predictions, and so on. So advances in science and technology really enable this evolution. So this is an example of to demonstrate the benefits of finer scale modeling. And this shows an example of a severe thunderstorm from 2009, so a number of years ago now. This is in the middle of the US, so Illinois and southern Missouri and Kentucky. And so this is the observed radar of what actually happened in this case. And you can see the National Weather Service operational guidance at the time was a 12-kilometer grid. And you can see it got the rain kind of in the right area, but not the structure of the feature at all. So it didn't really provide the detailed information that people needed to know in advance of the storm. So at the time in the research community, there was the Weather Research and Forecasting Model, or the WRF model, that was developed at NCAR that's used by the community. And at that time, this was being run with a 3-kilometer grid, and you can see that the feature is much better developed in this modeling. And so this kind of technology that was developed in the research sector is now being used in weather forecasts today in both the public and private sector. And you can see that even though the general feature is right, it's still in the wrong place slightly, so there's still room to be improved for the details of the weather forecast. So as I've talked about, weather forecasting is fine scale, and it's important to represent those fine scale processes in the models and also to be able to represent the weather where people live and what they experience. This is a satellite image from this hurricane season, which, as you probably all remember, was a major hurricane season. It shows Hurricane Irma in the center approaching Florida, which I'll talk a little bit more about later. And as you can see, weather forecasting is fine scale, but it's also global. So usually when people run a fine scale weather model today, it's usually over a regional grid because that's all you can do with the computational power and science available today. But the information that influences the forecast for longer than a few days comes from around the globe. And so it's important to also be able to produce a global weather forecast. So one of the innovations that's happening in the weather research community right now to enable this is global multiscale weather modeling, where you have one grid over the whole globe and you have a finer scale grid in a certain area that you're more interested in. So this helps you represent the fine scale in the area you're most concerned about, as well as the global weather processes that influence that. So this shows the model for prediction across scales, which is a community research model that's being developed at NCAR with National Science Foundation funding. So this MPAS model is a community model, which means that it can be used by the research sector, the academic sector, and the private sector. Anyone who wants to use it can get training in how to use it and use it for weather forecasting and for research. You can run this with a uniform mesh, so the same around the whole globe, or a variable resolution like I talked about. And it has a number of applications, but what I'll be talking about today is extended range or days to weeks forecasters on convective or weather scales. So how can you extend these small scale forecasts to longer lead times to give people more information to make better decisions? So this movie shows a 3-kilometer run from this model. As you can see, the model can really represent the fine scale features of the weather. If you think about this compared to the satellite picture I showed you earlier, you really can't tell the difference. It really represents the weather and its evolution at these fine scales. And if you look closely, you can see there's typhoons forming in the Pacific that are going to approach land. So this is really a demonstration of kind of the model capability. This isn't available to use in real time for weather forecasting yet. It still takes a lot of computational power and the science is still being developed. But this is the kind of innovation that's going on in the research sector that can help improve the forecast of the future. So as I mentioned, this model isn't used for forecasting for actual real forecasts, but it is used kind of to test out, to create forecasts in a retrospective mode to improve the model and to do science that will improve the model in the future. And so this shows an example of forecast from Hurricane Irma. The black line shows Irma's track, which you can see tracked from Africa west across the Atlantic and then north into Florida. And the red shows the forecast that was initialized about 9 days before landfall with this MPAS model. And as you can see, the forecast really got the track really pretty good for a 9-day forecast. This is something that wasn't possible years ago. This forecast is far in advance. As you can see, it didn't quite get the details right, but even 9 days in advance, it could tell us that there was a significant chance that this hurricane would affect the U.S. So the 9-day forecast is shown again, and as you can see, there's different tracks here, and those represent the forecast started at different lead times. So as you can see, up until about 5 days before the storm made landfall, there was information that the forecast was coming towards the U.S., but we couldn't really say exactly where the storm was going to go. So this demonstrates how further in advance you can show the envelope of what might happen, but you can't always predict the details, and this is due to fundamental limitations in predictability of the atmosphere. And then as you get closer, you can see that the 5-day forecast was pretty good overall, but it still didn't get the right location. And then as you get closer, you get more information about the storm hitting the west coast of Florida. But you can see there's still some differences in those forecasts, so it still shows that even a few days in advance, when people are making evacuation decisions and deciding what to do, especially for a storm that's going to cut across the whole state of Florida, there's still some differences, and that can be really important, which I'll show in a minute. So I've talked about the scientific advances, but as we all know, a forecast is only useful and has value if someone can receive the forecast, interpret it, and use it in decisions. So we also do social sciences research to improve risk communication and decision making. And we do different kinds of research, interviews, and focus groups. I've shown some examples from our research here today. One example from an interview is people tell us things like, I never could have dreamed of 7 feet of water, and they didn't know to protect their home from flooding for a hurricane. Another example, this is from Hurricane Matthew on the right, is someone who said, we knew about the risk in our neighborhood. We knew it could flood, but we didn't know what the flooding would look like. It was mind-boggling what happened and where it actually came from. So people don't really have that understanding of what it can mean for them. And these are all examples from members of the public. And then we also do some research with Twitter data, where we look at Twitter data during events to understand how people are interpreting the information and making decisions. So on the left-hand side, you can see this is an example of someone on Twitter who retweets information from a broadcaster where the broadcaster is saying storm surge may reach 8 feet with 10 to 20-foot waves on top. And this person tweets right back, what does that mean? What's it going to happen where I am? Define major flooding, please. And on the bottom right, this is some examples from a survey that we did where we tested different kinds of information. And people say, I want more specific information like the wind speed and the height of the storm surge. And it's not local enough. They want local information where they are. So next I'll talk about two other innovations that are going on now. And really, the first is predicting the hazardous conditions and impacts that people are experiencing, so the details of the weather and the impacts where people are. And then also how to communicate this information. So how can we bring these two ideas together to address these issues that we're seeing and how people receive and use weather forecast information. So this shows an example of forecasting hazards and impacts. This is for an example of storm surge, but you can imagine it for all kinds of other impacts like power outages and so on. And this is an area of emphasis in the weather community right now. So this on the left shows a simulation of Hurricane Irma, storm surge. You can see as the black line shows the storm as it's approaching, and you can see it produces surge near the storm, and it also produces a significant amount of surge along the Georgia coast, which actually happened. In fact, that area of the coast saw more surge than they did during Hurricane Matthew, which made landfall right near that area. So this is an example to show that it's important not just to predict the weather and the hurricane and where it's going to go, but also the different kinds of hazards and impacts that can occur in different areas. So on the right here, this shows an example from a different hurricane that made landfall in a similar region, but not the exact same place, what the storm surge looked like for that hurricane. And as you can see, small changes in where the hurricane goes can really make a difference in where the storm surge is, so where the highest impacts are and where the greatest risk to life is. And this is similar. This shows the difference that's similar to about the error in a 2 or 3 day forecast today. So it's really important to improve the forecast so we can improve the forecast of the impacts that people will experience and evacuate the right people from the right locations before the storm hits. So this shows a simulation using a visualization using the storm surge simulations I just showed to show what storm surge can look like as it approaches a local area. This, again, is a research product that we designed to test with people to see if this helped them visualize the risk where they are. And people really responded strongly to this and it helped them understand what storm surge can really do and how fast it can occur. This happens over about 15 minutes. We've talked to people after events that have run from the storm surge, and it's not fun. So we really want to get people out before the storm surge hits. And again, one of the challenges is to communicate this kind of realistic information and get people to understand the risk and personalize it, but also recognize the uncertainty on the timescale where people need to make decisions. You can't predict that this storm surge will actually happen in this location. So how do you communicate those different things together? So to conclude, here I've shown some examples from the different weather disasters that occurred in 2017. Like many years before, 2017 was a big year for weather disasters. We had major wildfires, we had major snowstorms that have major impacts on transportation. There are hurricanes, tornadoes, all kinds of things. And so no matter where in the country you are and around the world, weather impacts really are important, and improving the weather forecast can improve the decisions that people make and reduce the impacts. So if we continue to invest in physical and social science research, the kind of things I've talked about today, that will enable continued improvements to forecast information and decisions in the future for multiple types of weather hazards like I've talked about, and also for everyday weather, which also has a major impact on the U.S. economy. Oops, sorry. And so looking forward to the future, some of the next frontiers are really to do this, to have this physical and social science research investment in the context of the forecasting capabilities at different lead times. So the research that can help us produce forecasts at longer lead times and then go to predict more details as the event gets closer. And then also to communicate this information in the context of all the different ways that people obtain information as in today's complex modern world, like over phones and through Twitter and computers and so on. So next I'll turn it over to Fuqing Zhang, who will talk more about the research investments underlying what I've talked about.
happy lunch. My name is Fujin Zhang. I'm from Penn State, and I'm going to talk about what's basic science and how federal investment really can do, and how the collaboration between federal agencies and universities and academics really can help to advance our prediction of weather, in particular, very severe storms or hurricanes. So Rebecca just showed that models has been revolutionized quietly for the past few decades, almost 50 years, and the skills has improved a lot. But how does that actually translate to the things you care, like a hurricane track? To your left, it's a figure actually shows the error of the average in the hurricane track in different days, from 1 to 5 days. And what you see from this figure is one thing I want to highlight is nowadays, the 3-day forecast error in 3 days' time is actually as small as the 1-day error 25 years ago. That's really how many billions of dollars saved, literally billions of dollars saved just by those the track errors. And well, while we are making great strides in actually advancing the prediction of the hurricane where to go, but we actually haven't made a lot of progress in terms of how strong the hurricane is. It's actually part of the storm surges, hurricane high winds and rains is actually related a lot to the intensity and the structure of the hurricanes. We don't. That's the figure to the right is actually don't have a lot of improvement, except for the past few years, and I'm proud to be part of this program known as the Hurricane Forecast Improvement Project. And this is actually many federal agencies is actually complementary funding to do this possible. So I'm going to show you first what's possible. This is the HFIP project led by NOAA. And I actually one of the first ones is actually collaborating with National Science Foundation's High Performance Computing Center at Texas Advanced Computing Center. So at that time, they have 64,000 nodes, and our team was fortunate to offer 1 quarter, basically 16,000 computers running simultaneously for a hurricane analysis and forecast system our team developed and actually implemented in real time, predicting Hurricane Ike. And actually, that's the first time in history actually put the NOAA's Hurricane Hunter's Doppler radars information into the model. I'm going to show you in the next slide what it takes to get the better forecast and how to put the data into the model. This is actually a complicated slide. First, on the left, you will see this is NOAA P3, the Hurricane Hunter, and the P3 has a called tail Doppler radar. If you guys don't know what the Doppler means, the cops scanning your car's speed is using the Doppler as the phase shifter of the speed. But the Doppler is actually tracking every of those the hydrometers in the storm, and then they tell you how strong, how the wind, the flow. And that's that. And also, I'm also working with LASA, the Hurricane Science Centennial. That's actually Global Hawk is actually can be powered by aircraft. It's actually fly much higher. It's about 22 kilometers above, and then they actually do very high scans of Doppler and dual frequencies. In the middle, it's actually this drop size from both aircraft can drop this drop size, high accuracy developed originally by NCAR. And so you can see those of the type of the really critical data from the aircraft. By the way, the US now is the only country actually have the capability to scan with this high resolution Doppler and some of the technique. However, if you see this aircraft data has been around about 4 decades, but it's actually never put it into operational models to make the real impact to the public or to the society before our team actually get it in. So what we actually did is we actually take those data, we process it and thinning it so it allows it to actually come downwards to the ground in a faster fashion. And then we use the advanced data simulation technique, which is this red box. Sometimes you probably don't realize we have observations, high resolution observation, but those observations translate to the model. It's actually a very high intensity mathematical and statistical job, and people don't realize. And it's actually nowadays, most of the operational centers is actually data simulation and modeling is actually equally important. And at this point, I'm going to show you the slides. Data simulation is actually more important, contributes to our nation's GFS deficit than the model itself. So that's actually very, very important thing. What does data simulation actually means? It's actually advanced technique how to actually take the observation. Yes, you have Doppler radar, but you actually don't observe everything in the hurricanes, and you don't observe everywhere. So what you do is actually you take this spotted data, and in a certain areas, you propagate to the whole model domain to propagate to the area of this variable, like wind, humidity, moisture, especially moisture, because moisture is really hard to observe in the atmosphere. And that's the data simulation process. You put it in the model, so-called model initial conditions, and that actually powers the forecast models. So both are equally important. So our team developed the so-called Penn State WRF ensemble common filter system. And the WRF model is the NCAR, originally developed with NCAR. And this is actually slides which we actually run this system in experimental as part of the HFIP program in real time from 2008 to 2012. We showing here more than 100 P3 tail Doppler missions we do for every of these cases. And to this graphics, now the arrow is the forecast intensity arrow in terms of lots, right? And then the blue line is actually the National Hurricane Center's average forecast arrow for this 100-some realizations, okay? And the red line is our experimental future system. You can see for the past few decades, we don't see much improvement in intensity forecast, but with this high resolution data, advanced data simulation technique, with the high resolution model, we will really be able to demonstrate the hurricane intensity forecast error can be reduced as much as 30 to 40% from day 1 to day 5, with potentially even longer. So there are a lot of room for estimate. By the way, working with NOAA, currently this technique, actually the tail Doppler, our methodology has been adopted by NOAA, and it has shown significant improvement in the operational forecast, so-called HWRF. However, this is actually a rare case. Many times the university developed technique, it's actually very hard to transition to NOAA. There are funding issues, there are barriers between agencies. So those of you can make a difference in the future, hopefully, and that will. But it can be done. And this, many of you probably contribute to this big effort. It's actually a National Science Foundation has a big data joint press conference about with the White House, and it actually does show our products and actually make a difference. To your figure, it's actually Hurricane Ike. We actually really produce this forecast in real time with 16,000 computer cores together running and make those forecasts. It's actually pretty historically first time done there. So my next love, or the things our government funds, NASA develops the GOSAR and now already transitioned to NOAA. And this really, the GOSAR is, I think it will be a game changer in many ways. As you can see from this figure I borrowed from NOAA's website, the future of forecasting. However, I want to warn you, many of the satellites we US have the best satellite. And we have launched so much satellite. But most of the data actually has not been used in the models, in particular for the areas we actually care. The so-called all-sky radiance. Actually, US models now not have any impact from the so-called all-sky. What does the all-sky means? The cloudy area, the rainy area, those are actually critical for hurricanes, for severe storms. Our national model is incapable, is inferior to take those data at this point. And we are really underfunded, underinvested, and underpowered compared to our competitors in the European centers and UK Met Office. So that's something I'm going to show. It's actually, there are a lot of promise. The next slide is actually for Hurricane Harvey. You guys probably, just like me, have fresh memories of how I actually used to teach at Texas, so that area is so dear to my heart as well. And this I'm going to show you here is actually just a few days. This is not real time, but near real time. A few days after the storm, we actually, because this is the first major hurricane actually captured by GOSAR, and to your left is actually an independent observation. The GOSAR has 16 channels to cover the radiance. And to the right is our WRF ENCAF analysis of the storm. If I don't tell you ahead of time, you probably don't know which is actually observed, is actually simulated, but also side by side exactly compared. They are almost identical. So this is actually tells you the GOSAR next generation with this advanced technique and with a high resolution, you really can integrate the model with the observation. This actually allows you to do forecast I'm going to show next, but also allows you to do many high intelligence mechanisms to actually predict the hazard and other things. So this is actually the still picture at different, this is 6 hours. Only 6 hours, every hour you assimilate those data, you can see you almost get it. And then this is 12 hours and 24 hours. That's before, and that's the time we actually used it to initialize model and actually tell you what's the impact you can see. So to your left is this hurricane track forecast after, so the orange line is the ones that actually just without this, without GOSAR data. And then the red line is with the GOSAR data. You can see dramatic improvement in the track. But more proudly, for my effort, is actually focused on hurricane intensity in the structure. Look to your right. You can see 2 days before the hurricane make landfall, or almost 2 days before hurricane make landfall, the Wolf model, which developed at NCAR, initialized with the GOSAR and using our data simulation system. Power that you can see, you can predict the major hurricane even to a category 4, almost the right time and way ahead. And also the ones, the orange line, without the GOSAR, you don't get it. Just for reference, our operational forecast model is actually taking some aircraft observation. It's actually pretty good, which is the blue line, but nowhere to even make a major hurricane. So the next slide is we actually moved further, and Rebecca says the global model. Well, we're actually working with the NOAA's GFDL, the Geophysical Fluid Dynamics Laboratory, developing the next generation model called FV3. Our team working with their team, and then we actually also put a list of this model. So basically a global model with the high resolution, that's 3 kilometers. And we use our Wolf analysis, ENCAP analysis with the GOSAR, and actually initialize the hurricane in this global model. And then you do a forecast. Literally the same forecast as I showed you before, just 2 days before hurricane make landfall. To your left is a model simulation. To your right is actually a real observation from ground-based radar. Literally, you can see how possible promise you can actually do with even the model 3 kilometers for this particular storm, the eye wall, you're probably not going to resolve the detailed eye wall, but the rain bands and the location is really remarkably 2 days in advance where it is, and even the structure into a great extent. Obviously, you remember for Houston, it's really the flood, okay? And this is actually 6 days forecast of the 6-day total event total forecast of the precipitation. Well, first you might want to say, oh, to your left is actually the FV3 models. You might actually say, oh, you missed Houston by quite a bit of the difference. However, considering 5-6 days forecast track is a still considerable error. You shouldn't literally put that things in that place. But if you consider the track in uncertainty, and that to your left, 6 days in advance, you predicted about 40 inches of rain. It's almost unprecedented by a model. It's a global model. And in the general proximity, and you see the landfall time in Corpus Christi, it's almost perfect. And then to the southeastern Texas, it's just remarkable, even though, yes, in the actual observation, it's slightly higher, but it is remarkable what we can do. Just trying to hammer home about this data simulation. Some of you may not familiar with this terminology. I want to show you what really drags our nation's capability in terms of every time you guys probably like me tired of hearing we are far behind Europeans, right? I'm really bad to hear that. I say we are pretty good, but our ideas hasn't been implemented as much. We don't have the resources to do that. For this figure, This is actually produced by NOAA GFDL and actually independently verified by my friends at ECMWF, Ninas Magalasan. So what you show, this is actually a complicated figure, but I want to take home message is, so there are 3 lines. The first line is the red line. It's the official European forecast performance called anomaly correlation. What does that mean? Anomaly correlation, you verify with their own analysis. If you correlate with the analysis considered to be observation, if they are highly correlated, it means your forecasts are good, right? So that's the anomaly correlation. So this is from day 1, day 0 to day 10, 240 hours, okay? So what do you actually see? The second line is actually the next generation models, the FV3, powered by the current operational model's initial condition, NOAA's initial condition, the operational initial condition. So, which is actually green. As you can see, after about 2 or 3 days, we're lagging behind, and we are further lagging behind, and we're back. It's actually around 7 days, we're at least 1 day behind. You know, 1 day translates a lot of money. Barry is in the audience. He knows that accurate forecast is very important if you get even 6 hours ahead of time. But this hour really, it's the same model, but it's actually with just the difference in the initial condition. The initial condition, as I told you before, is due to the data simulation, how you ingest the data, how much the data simulation algorithm is that. So, well, help is underway. The FV3 model, the blue line, if they are actually using the European model's initial condition, run with the FV3 model, you can see from day 1 to day 5 or day 6, they are almost identical, comparable to so the red and the blue are almost the same. This is the first time the US model can beat the European model. Is after about 7 days, the US model the next generation model is actually can be ahead. And that's the future promise. So I'm going to conclude the slides the same. As probably obvious to you, I think there's lots of promise and there's lots of leads. And I think the federal investment, to me, in the academics, I will be proud of doing the things and transfer things. I hope that the channel still opens to take home message, how to make a better forecast of hurricanes or severe weather or anything in this Earth system. You have better observations, which is like a radar and satellite, especially the newer small set and also unmanned drones. And the model, you need a good model, obviously. But the data simulation, many of you probably the first time you heard the terminology, it's a cook, how to make the models into, how to get the good data into the model's initial condition to a good forecast. Obviously, computing, and I didn't put the personnel. We need high-powered students and scientists to really do the work. Thank you. Next is Mary Gleckton. I will have.
Thank you, Fuxing. Okay, it's my job to bring it home. There's still sandwiches here. If you didn't get something to eat, grab it. You won't insult me by going up there. Okay, so it might look a little funny to have IBM buy the weather company. We were bought just about 2 years ago, and the reason we were bought is the recognition that really weather impacts every consumer and really every business on this planet. And we've been on a dedicated mission to serve those. So currently we have more than almost 4,000 businesses that we serve in over 70 countries, and we're rapidly expanding that. And we have the largest consumer-facing applications because we're powering things like Apple, Facebook, Samsung, and other things. So we do this, we handle a lot of data, and with respect to weather, it's always important about being precise in that regard. So Rebecca made some really good points earlier, and it's ones that we think about every day in business. We're not really in the weather business, we're in the decision business. So we're dedicated all the time to whether you're a consumer in understanding what maybe some of your lifestyle choices are and helping you make a better decision, or whether you're a business using your business data and analytics to do correlations among them. So it's what drives us to do that is to have people make the best decisions with respect to weather. And I think the point, too, we focused a lot here today on extreme weather, and I will as well, but the everyday weather makes a big difference to help businesses optimize in various ways. So how do we do this? So we use, I'll say right up front, a lot of public source data, including those from NOAA. I mentioned before, a large consumer face to our business. So on a daily day, we're servicing about 45 billion requests for a weather forecast, and we deliver all of those from a local perspective. If you think of the globe, we have about 2.2 billion points mapped around the globe, and we'll return data at that kind of precision. And obviously, we deal with a lot of data to do that in terms of ingesting all sorts of observing sources, and we have private sources of weather data as well. But we take in virtually all of the publicly available weather information, weather observations that are out there. So we've heard a lot about models, who's the best, the European, the US, et cetera, et cetera. I think that probably most people in this audience know that we have ensembles of models now. We'll take the same model and perturbate it a number of ways and run at different times, and you get a better answer that way. So when we think about weather forecasting, the approach that we have used is really to take in all of NOAA's operational weather models, the Europeans' weather models, some of those from other countries that are available to us, Australia, Brazil, Canada, et cetera. And what we do is really a dynamic machine learning application on top of that actually has its roots back in NCAR from around circa 2000 there. So in real time, we're taking in 162 model runs multiple times a day, and we use a dynamic machine learning approach on that to come up with the right solution. We continually update it every 15 minutes with new observations, data coming in, including we have a personal weather station network of 260,000 sites globally that feeds into this. And we've recently been also using cell phone pressure data from various cell phones. So that's a little bit of a backdrop in kind of our forecasting technology. One of the models that we do run that's part of that 162 there is we're running a current version of the WRF model, which each of the previous two speakers have mentioned. It's the community-based model that we have in the U.S., developed and housed by NCAR. So we're an active participant in that community. We check code out of it. Our scientists will put some of the code back into it. And then we keep enough to make ourselves have a proprietary commercial viable solution. We announced this summer, and we're really excited about it, extending the partnership that we've had with NCAR. And it's actually a three-way partnership between the weather company and then the IBM computing folks. These are the big brain people in IBM research that are working on next generation of computing architectures. And what we're doing is moving to market with the MPAS model, which Rebecca talked about, for all the reasons that she listed. And we have that version of that model now running in our laboratory and expect to have it out operationally next year. So we're looking for a very high resolution to run on this globally. And we'll be sharing back with the community our results in using the next generation IBM research, IBM compute architecture, which is a combination of CPUs, computer processing units, and GPUs. And as I said, we've been working collaboratively with NCAR on it. So I want to come back to this industry aspect, which I was asked to speak to here and talk, kind of keep up the the topical theme on tropical weather, but kind of talk about it from a business perspective. And so there's a number of businesses we serve when there's tropical threats, but I thought I would kind of focus on insurance today. And this is one of our major sectors. We do a lot of work with insurance industry. For example, we're able to give hail alerts and working with the insurance company, deliver them right to consumers, the clients of the insurance company, and have them move their car into garages and things like that to avoid damages. So when we start to look at that from a tropical perspective, the engagement with businesses actually can start out in the seasonal time frame when we're making some predictions about what kind of active season it is, which will inform a number of business decisions. But coming in a little bit closer, starting about 15 days, there's a real interest from insurance companies about their exposure there, and they have to make decisions about whether they're going to buy reinsurance because of their exposure in a particular area. So those long-range forecasts that we've talked about here today are tremendously important. That kind of, so that starts in the long time frame. And then, in days in advance, they're trying to make decisions about deploying insurance adjusters into particular areas so they can be responsive to their clients. And so how they make the right placement, we're advising them on things like that. And then finally, after the post-event, there's also work that's done with respect to stopping fraud, verifying claim information with respect to fraud. So that kind of work has been done traditionally for a long time, what's really by forensic meteorologists, but we're now leveraging some of this big data and machine learning to automate a lot of that work so we can quickly make decisions on that. So it's I hope you see it's a really rich kind of set of uses that comes out of really basic federal investments in observing and modeling that we translate into more effective business decisions. I want to talk also, I mentioned we have a large consumer face with our web and mobile presence. And in this case, we think of it as a shared safety mission. So we are dedicated, like most of the U.S. weather businesses, to redistributing the alerts that the National Weather Service issues. And we do that without alteration and with attribution. We actually do this globally for any Met services. We really want to deliver the alerts from the Met Service itself. But it's an area that I would really highlight and really as one that we need to do a lot more work in. I would argue that the forecasts were quite skillful for Harvey in terms of precipitation, multiple days in advance. And I think that we're not conveying the risk and the impacts to people that is motivating them to take action. So I feel like we're a little bit issuing a teletype forecast in a world of digital and not really getting the response. So the work that Rebecca mentions, I think, is tremendously important, and how people get information is changing, changing rapidly. So when we come at it from a paradigm of the 1960s, it just doesn't play as well in this time. So I think I see real gaps in that area. Finally, with my co-panelists here, I'll just offer some of the key takeaways, and then we'll be happy to and hope that we get some questions. The first is that we contend that the federal investments really do in this area tremendously propel the economy. The world would look nothing like it did today without the very skillful forecasts that we have here. At the second time, there's really key physics and social questions that remain to be solved. So there's research left to be done here, much of what's been described by my colleagues today that I think would really return incredible investments. And then finally, it's about public-private partnerships that ultimately you want to keep people safe. And that's getting more and more complex as people live with respect to all sorts of hazards in areas that are riskier than they once were. And I think it's going to take a public-private partnership to address those things. So I'll stop there. And as I said, I hope we can get some questions.
Thank you, Mary, and thank you, Fuqing and Rebecca. And so we have about 20 minutes for questions, so please take advantage of this expertise. Please.
Sort of building on what you were saying, Mary, what specific areas do you think would sort of be beneficial to have public-private partnerships for the social science and communication? Or do you think there's a danger there of sort of mixing up the roles and maybe dropping the ball? Do you think there should be defined roles, or can it be more mixed?
Does this work? Yeah, I think that it's actually really imperative that we come together to envision a better service than we have right now. And I think it's more complex than just redefining products that we have. So I think that the private sector, we are not the only company, there are other companies able to do this too, that I think have a much better feel on how people are consuming information. And, I think we've looked at this too much as a warehouse chain of putting information out, and we need to come back and look at it in terms of how people are actually consuming information. I think ultimately, I think we went through our little crisis in the country in the 80s and have come down to we want a single source here. We don't want to confuse people. It is complicated, though, because as a private company, we advise businesses, that have employees too, so it's hard to contain things, in that regard. But I'm fairly confident. I think we have a lot of maturity in this country in working together across the various sectors, public, private, and academic sector, to bring to bear here.
Yeah, so I wanted to add to that. I think that the way that people obtain and communicate and interact with information is changing so rapidly today that we really need to have an adaptive system. You can't define roles and kind of keep them for all time. It really has to be adaptive, because by the time we understand what the best thing to do in any situation is, it's already changed because someone's invented some new platform or everyone's moving to something new and so on. So I agree with Mary that this is a really important area and that we need to develop something that we can adapt as things change. And the private sector is really nimble in terms of they have to respond to how people are changing how they use information in order to stay competitive. And so to bring some of that understanding into the public sector, could be useful while maintaining the advantages for the private sector. I also think that with more weather forecasting information available today, people are getting new information all the time, and it's changing really rapidly. So I think really the best avenue is to bring the physical science and the social science together, because the weather forecasts are changing, how people use them are changing, how people make decisions are changing, and so that's what you really need to do to produce better weather forecasts and better decisions.
Gary.
I want to thank everybody for your comments. Quite interesting. Mary, you mentioned you have access to pressure data from cell phones. You're sending those data to phones. And I think I saw you say 100 million. Do you make agreements with all of the cell phone owners to do that? And also, what difference does it make in the forecast with and without the cell phones?
So the answer is yes. We actually have a triple, when you take our app to do this, you actually get 3 times you get asked about us using information from there. So yes, and we're soon going to be compliant with the European. Europeans have a much higher kind of standards for this called GDPR. I forget what the acronym stands for right now, that we'll use globally. So we're completely adherent with all of that. I think the thing on cell phone pressure data, we're on the cutting edge of this, so I'm not going to give you any numbers today on that, but we can keep talking on that.
Other questions?
Jane, you mentioned about personnel and how important federal investment is on that front. Are there specific areas of STEM education, gaps in having the right professionals? Are you seeing the students that are graduating, are they meeting the skill sets needed in the field? Or interdisciplinary in that front, or where are they?
Well, that's a very important and interesting question. I don't think the U.S. system is deficit in terms of that. We obviously needs to educate more people on how to do the data simulation. It's actually you need to know physical science, mathematical science, and many things together, and also instrumentally how to calibrate zones. But in general, the U.S. actually produced, I'm confidently say they produce the best scientists and the best students in this area. However, our government structure currently doesn't appear to promote to have a high powered and caliber. They are always there. I don't want to hurt anybody, but I think the current system, our system don't have this word top large or doesn't have as many as needed at this point. And there are several barriers in terms. One is how our federal system is incentivized to have the national center and how NOAA is developing the data simulation. There are a lot of expertise in the universities and haven't been used, and I'm one of the rare ones that actually work and find the things I develop. I'm proud to be actually working into the operations. But many times, the researchers and scientists find it frustrated that their ways cannot be simply adopted. One other thing is actually the ways how our federal government is funded or fund different researchers, because the university researchers are advised not to put too much operation. It's actually the National Science Foundations and advising the university scientists not to spend too much time or money on the operational side. So that's actually another barrier, because that's, and then the NOAA is saying, as far as in the past, is you really do something, it has to be really quick to come to my shop. And what you develop, you provide me, you have to actually provide the ways to actually help me implement. And there are lots of barriers, and I think that barriers needs to be break down. I don't think the U.S. is short of education or short of brains. We just segmented, and we don't have ways to unify systems to do like what's. I hate to bring the Europeans. They actually really consolidate one center, one mission. They are much more efficient in that way. So again, I think it can be done, but we haven't been done well yet. And our federal system currently set up, it doesn't appear to allow that kind of center of excellence as easily as possible. It has been, but sometimes it has a lot of barriers.
So I wanted to add to what Fu Ching said and say that I think we see a growing number of students today at the undergraduate and graduate level who want to do interdisciplinary research. A lot of them love science or they love the weather, but they also want to do something useful, and they're trying to find ways to do that. And I think people are being successful in finding ways to do that, and Penn State has a program in this and sort of training students to do that. But I think a more coordinated effort in that area would be really valuable. Right now, each person kind of has to find their own way often to do things like internships at private companies or internships at NOAA, so they can, while they're figuring out where they want to go and what they want to do, they can learn from different sectors and be mentored, and also be mentored in how to kind of take all the knowledge that they have. I mean, the students today are the ones who have the experiential knowledge where they're all on their cell phones all the time and they are in this new communication world. And I think they can bring a lot to the scientists in terms of how to use that kind of data in the modeling and how to communicate that kind of information. And so sometimes they just need kind of the right mix of experiences and the right mentoring, and some organized programs in that fashion could really be beneficial.
Taylor?
You talked about the next generation model, the FP3, and how it compares to the European model, and maybe slightly be better. But what about the European next generation model? Do they have any plans for how they're going to be keeping up with us?
Oh, they do, and obviously every center is just like somebody mentioned in the UK matter. They all have things in the pipeline, but just like currently the FV3 model, if you can actually have the good data simulation, you can run it now. It already is there. It's already there. We're running the current US GFS resolution, so even slightly lower in resolution, your score is already up there. That's one thing I've got. I mean, it's remarkably people don't realize this, how the data simulation is sophisticated. Actually, the models usually with the physics developed by a different team, but mostly the model dynamic cores actually need a lot smaller team. But the data simulation requires a lot more. Each of the satellite channels, it actually requires a personnel dedicated to know how to do those things. And again, the US now have less than 1% of the data being used in the models. And we put up a lot of observations. We rarely, the federal funded so many good satellites, but rarely they fund people to use this. So you guys hopefully can pass this message because research needs to be done in how to take those data. Just those good materials is not good enough for food, right? So, simple.
So if I were a competitive patriot and I wanted to get us over the top and push our model past the Europeans, and if data assimilation is the answer to that, who is funding it? Where does the pipeline, how does the pipeline flow? Clearly there's some great people at the university level. How do they get their funding? What agencies are active in this area?
So I do data science. My group probably is the biggest single university investigator in the area of data dissemination. We are funded by NOAA, NASA, NSF, and ONR. However, most of the things we are funded to do is actually under the name of doing science, of the physics science, but we really, actually, there is no really great channel to fund data dissemination except for NOAA. And NOAA, when they actually trying to fund something, they actually want something to be so quick in the 2 or 3 years. You actually need a chain of longer-term development and short-term development, and currently we just don't have that. And also there is a barrier between operational systems with the university researchers because of the computer, how university researchers. Without this H5 program, our team will not be able to access the speed computing, and also now team actually have the same, was able to run on the NOAA computers, and that's actually makes all this available. Most of the university researchers cannot do that, not because they are not capable, because they are not funded or not equipped to do many of the things, great things in head. And again, that's a gray areas of the data dissemination are not really funded by anybody. They are funded by everybody, but on the other hand, they are not targeted by anybody.
Rebecca?
Yeah, I'll add to that and say that I didn't mention this in that Bauer et al. Paper that I showed about this quiet revolution of numerical weather prediction. They talk about how the achievements in numerical weather prediction over the last 40 years have been, a coordinated effort similar to putting a man on the moon. I don't think it's that much level of effort to improve the data assimilation, but in the U.S. we definitely have the scientific capability, we have the technology, we have the knowledge, we have more than enough kind of intellectual power and capabilities to do it. It's just that we haven't had the coordinated effort to really invest in this area. And the advantage that ECMWF has is that they have a coordinated effort that's focused on assimilating the data. And so I think it's just a matter of, and there are groups that have kind of tried to do this with the different agencies working together. It's just a hard problem when you have so much expertise, in fact, in the U.S. Maybe that's one of the challenges, is there's so much expertise that everyone, wants to have their thing, but a coordinated effort with real leadership and investment with that leadership towards a common goal could really make a huge change in just a few years, I think.
It's no secret in terms of both the model development and data dissemination development is actually sometimes my ideas or our ideas is easier to be implemented in European centers than our own federal agencies.
Gary?
Yeah, I want to follow up this European versus US. And we're not acting in isolation when we do our research on data assimilation or even physics of severe storms. Everything's published in the journal. If you want to find out what the latest is on data assimilation, go to the journal, whether it's published from a European investigator or a U.S. investigator. There's a lot of collaboration between ECMWF, Net Office, and anybody else. So what's the barrier? So we exchange information, we have access to all of the developers on the European side. We can run their models as visitors at the European Center, they can run ours and visitors. Why are we behind? What is that barrier to kind of keep us on the same par? We kind of do that dance, but each side can go stepwise and make progress.
I don't know whether I should, because Mary actually have a lot of experience at NOAA. But if you want to be blunt, our current federal, especially NCAR, who wants models, they actually don't have enough expertise and enough manpower to actually implement all the brain powers available in the U.S. universities. And it's very hard channeled, hardwired, how people actually can contribute to that system. Things has been changing, but data dissemination is actually what you say is actually very interesting. When you saw it in the journals, usually 2 or 3 years old, actually you're going to be behind by that much already. So not really just that, it's really a development, and there are several things. They are very currently, what we find from the European Center, we have done these comparisons. They are ahead by using the amount of data probably by 4 or 5 years, and then they'll by their data simulation system by a few years, and then you overlap some of the overlap. So they are basically their NWP is about 5 years or to 7 years ahead of the US. So they are actually quite ahead of us, and partly because of the model. But if you put the next generation model in, and the data simulation system takes much longer to develop, and we don't really have actually a clear objective at this point. What's the data simulation framework we're going to use at the National Center for Environmental Prediction, as far as I know? I might be limited, but I do talk to everybody who is involved.
Yeah, I think that's well said.
All right, so we have to vacate the room at 1 o'clock. I'd like to encourage you to follow up with any of our speakers outside, but I hope what you've seen over the past hour is that the investment in basic research by the agencies, by the taxpayers, is making this transition from basic research that's providing actionable information that's leading to informed decisions that the private sector is taking advantage of in a very positive sense for the betterment of citizens in the U.S. and around the world. And yes, we have our challenges in front of us, but I think what you've heard here today is that if we have the will, they are not insurmountable. I mean, we do see the light at the end of the tunnel. It's not a train. But we need the will, we really need the will to take advantage of basically this whole value proposition that's Mary put up on her last slide. So please join me in thanking our speakers here this afternoon.